I did the first applicant, so I combined the two in the engine, and then the next is animation.
Okay, welcome everybody. It's time. How are we doing? We are barreling into the end of the semester, and I hope you're doing okay. There's a lot going on, a lot of stress and strain. Okay, sorry. Do you see that we are in session 21? We only have today and 4 more opportunities to have this face-to-face experience. Isn't it precious? And you're probably like, good riddance. Now, we're gonna have a good time. We have some very important topics to cover. Criteria, failure criteria, which will essentially tie a lot of what we've been discussing in terms of transformations, in terms of combined loading, in terms of different structures, in terms of material properties, all together to be able to determine whether or not something will fail. So that's what we'll do in the next week, the next couple sessions. And of course, if we're able to determine whether or not something will fail on paper, that means that we have a design tool to figure out whether or not we should change the design or how we should manipulate it. So hopefully we'll find the tools that we've introduced in this class useful for the rest of our careers, or at least part of our careers. And if nothing else, useful for the next class in the prerequisite series. So after that, we'll go back to beams. So we have beams 4 and 5, where we'll finally, did you notice maybe you didn't notice, but for bars and for shafts and rods, we have that equation that delta is equal to PdX over EA, right? And we have that integral of the angular rotation is equal to the integral of T dx over jg, right? We have those integral equations, and we have the PL over EA, and we have the TL over jg, all right? So we know something about the displacement of those structures. We have not talked about displacement or deformation of beams yet. So that's where we're going to go. That will be the final treatment in this class. Okay, and then the final exam is on the 17th of December at 8 a.m. Okay, and we will be hopefully, as long as everything is still good. I don't think scheduling. There were some things that we were discussing with scheduling. As long as no one else is taking that room for final exam, which I don't think they are, then we should be able to split ourselves again in those couple of rooms. Any questions about where we are in terms of the timing or the administrative details of the class? Okay. Yes?
Is the final going to be split the same way the midterm were?
Yeah, it has to be, essentially, because we don't fit in here.
But we can still switch to College Ave.
I would love for people to switch to College Ave. All right, if you want to move to College Ave, let's do it. All right, please, because I think your friends and other people, we're friends, right? But we would like a little more space in this room. Okay. Other questions? And just a plug for College Ave. It's roomy, it's new, it's nice, it's enormous. Okay. Okay, well, there was another question. Was there another question? Okay, there are some things to keep in mind in terms of due dates. If you have not submitted your lab and you did do the lab, please submit it before the final day of classes. Those labs are due essentially the final day of classes. All right, so if you haven't done that part yet, do it. If you have questions about how to handle the lab or how to handle the data, perfectly game for office hours. Okay. I think Rebecca's been doing a great job with the labs. I hope those who have done the lab have found it somewhat useful and interesting, especially as it relates to material properties. You will have other labs in measurements, in senior lab, that do make use of mechanics. All right, so this is not the last time you do a mechanics-related lab. You'll get to do a strain gauge lab in the future too, and we're going to talk about strain gauges today. In terms of other things that might be due, of course, we're in the middle of grading exam 2. Please don't openly discuss it yet in the group me. There are some folks who had extenuous circumstances, so let's keep it on the down low for now. That said, once we've got those labs, or not those labs, those exams graded, once again you'll be able to turn in a request for regrading, all right, which you did for exam 1. That is done. Okay, that's done because that was due by exam 1. And yeah, so please, if you have requests for regrading on exam 2, get those in, promptly before the end of the semester, preferably. Okay, or before the end of the classes, preferably. Sorry. Yes.
Do you think that they'll be graded for the break or
before Thursday?
Before Thursday this weekend?
No, I don't think so. We'll see. Okay, but let's plan on having a happy Thanksgiving. All right, and then the week after, I think you can anticipate receiving them. Okay. Any other questions? Lots of talk about the administrative stuff. I just want to make sure we're on the same page. Once again, we have office hours. Praj and I do at separate times. I have my office hours after this class and on Fridays in D103 and over Zoom. Okay, so and people have come and talked to me both over Zoom and in person, and it's a pleasure to get to know some of you. Okay. Great. So let's go. Let's get this show on the road. Plane strain. You may be tempted to use a different type of plane, but this is not your vanilla strain. This is your planar strain, okay, that we're going to be talking about. And today we're going to discuss plane strain and transformations, and what the difference between plane strain might be and plane stress might be. We'll also use more circle again with our examples of plane strain, and there's a little hiccup that sometimes throws people off, and that hiccup is, let me get the laser pointer, it's right there, okay? Foreshadowing, it's the gamma xy over 2. And that's what you'll see, it's right there too, gamma xy over 2. Okay, so the y-axis, we're going to say this multiple times, but this will be the first. This gamma xy over 2 represents the vertical axis. Okay, before that would have been what? If we were doing plane stress, that would have been tau, right? But we didn't do tau over 2. Okay. But here it's gamma over 2. And that's because of how the math works out. And then we'll get to discuss strain gauges. Has anyone used a strain gauge? Has anyone measured strain before? Yes, what were you measuring?
The load on a cell.
On a hotel?
Load cell.
Load cell. Okay, so wait, hold on. We just said two very interesting things. We said load cell and we said strain gauge. All right, so what was your configuration? Because load cell, what does a load cell measure? Load, typically, right? So you're typically measuring a force or a torque. Okay, what does a strain gauge measure? Measure strain. So what was, without disclosing any, proprietary secrets, what were you measuring with your strain gauge in your load cell?
Well, I had a Wheatstone configuration.
Okay, Wheatstone bridge, good. All right.
And yeah, it was just like, as the load was pushed down, it stretched the strain gauge, which caused a change in resistance.
Okay, well, but the strain gauge was on what? What was it on?
It was on the load cell.
On what?
The load cell.
on the load cell. Okay, so what was the structure?
Oh, so it was a ball.
Yes, okay, see, that's a critical piece of information we're getting, right? Okay, so you were loading, was it a beam? Were you loading like a beam, or were you loading it in tension? How were you loading this bar?
It was a beam, and then we applied a load over here, so it was putting the strain gauge at the top of tension and the bottom.
Excellent, so now we've got it. And was this 3-point bending? In other words, did you have essentially a pin on the side and a load cell in the middle, pushing down?
Clamp on one side.
Okay, so it was a cantilevered beam, all right? And you had a force being applied by the load cell that was telling you how many newtons or how many pounds of force, right? And then you had the strain gauge on the top and maybe the bottom of the beam, and that was telling you the strain at specific locations, all right? Thank you. Lots of information there, okay? So that is a perfect example of how you would use a device for measuring strain. It's very hard to measure stress directly. Why is that very hard? Well, it's kind of this, you're asking us to measure a force without, over an area, and yeah, it's just, you can't really do it very easily. But, maybe you have, there are optical techniques, like if a material is birefringent, it has interesting properties, we're getting off into the weeds, folks. But a material that has, for example, has some transparency, like polymethyl methacrylate, acrylic. Okay, so that's a material where, as you put strain or load or stress on it, it can change its index of refraction locally, and then you can see that if you use polarized light, you can see how it affects the ring patterns, right? Have you ever, so in our neighborhood, they recently put up new basketball hoops, okay? And the old ones were metal, right? But these ones are nice, clear backboards, right? So that's like an upgrade, right? They are not glass though, okay? And how could I tell they were not glass? Because they had drilled holes through them. And as the sun was going through it, I could see all these birefringent patterns. So you were able to kind of visualize the resulting residual stress in the material. Okay, so I was kind of cool. I was like, well, I'm a nerd. I know what's going on here, kind of. Okay. And yes, the backboards, I think they do better at absorbing a little bit of the energy from the balls, right? They don't go poof like the metal ones often do. Anyway. So that is kind of a technique that people will use to show stress and strain. It's very hard to measure stress, though. Again, it's very hard to quantify stress. It's much easier to quantify strain, though. Okay? And the basic idea for quantifying strain is what? That, well, I have some change in length over the initial length. So if I have an instrument like this, or a sensor like this, right? I can plaster that onto a structure, and as I load that structure, I can see how that gauge, okay, now this gauge has a different meaning, right? We've talked about gauge pressure, we've talked about gauge length. This is an actual gauge, as in it measures something, okay? This is a strain gauge. At least in the US, I would spell all of those with a G-A-U-G-E, okay? So this is a very nice device that will tell us what the strain is in an axial direction. So they typically are designed, each individual strain gauge is designed to measure the strain in one direction, and we use them in combination with each other to get the 2D state of stress, or the 2D state of strain, better said. And then we can maybe back calculate what the stress is. Okay? So hopefully today borders on, yes, some new theory, but also a very practical engineering situation where we want to quantify the effect of a load on a structure. And we're quantifying that in terms of the strain. And we could put strain gauges at multiple locations. Okay. Any questions on this? All All right, so let's continue now and get into the details. So plane strain, okay, is going to be a representation of the state of strain, and it's going to refer to a particular type of condition. But before we even get to some of the details on plane strain, let's just say that a field of strain could be represented by our familiar buddies. Okay, we have our epsilon x, our epsilon y, our epsilon z, and we have our gamma xy, our gamma xz, and our gamma yz. Just like stress, 6 different parameters to quantify strain in 3 dimensions. Now, with plane strain, we're typically referring to situations where there are thick plates, okay? And we will take some liberties in going between the plane stress condition. If you recall, plane stress was typically for very thin plates, okay? Like the pressure vessel, the thin-walled pressure vessel. Okay? But in this case, when people talk about plane strain, you think, I've got a lot of thickness. And we're saying that just like we had in plane stress, the z direction, right, the component orthogonal to the plane that we're looking at is going to be zeroed. Okay, so in plane stress, it was sigma z was equal to 0. In plane strain, we're going to say epsilon z is equal to 0. The shear strains perpendicular to the plate, the xy plane, right? Those are also going to be 0. So gamma xz and gamma yz, okay? Those are going to be the zeros, right? So we're just left with the epsilon x, the epsilon y, and the gamma xy. That's what we're talking about with plane strain. And the plane strain is going to be thinking about what's happening in the plane, all right? And if you recall, we have a pretty good idea of what epsilon x looks like, all right? So we have some displacement divided by the original length. Epsilon y would be orthogonal to it, where we have some displacement divided by the original length. And I didn't write original length and I didn't write displacement here, but what I'm getting at is that we have some little delta x, right? And we had some original x, or some original Lx, right? And so epsilon x could be said to be equal to the delta x over the Lx. And same thing for epsilon y. Now, recall that the shear strain is a little bit different. Okay? The shear strain is described by the angle of deformation in, whoops, I hit the wrong thing, in the corner. Okay, so you see this corner here, which let's say the right angle corner. Okay, and what we often do is we say that over here on this side we have a gamma over 2, and on this side underneath we also have a gamma over 2. And another way to look at it is that the gamma xy is going to be equal to this 90 degrees minus the internal theta, right? So all those ways of depicting the shear strain are valid. Notice, this is depicting a positive shear strain. So if there's a positive shear strain, the corner goes like that, at least the corner of interest, okay? And like this would be the x direction, this would be the y direction. And so this is this describing what's happening in that corner. The angle is larger, okay, the resulting angle is larger in these other two corners, and it's smaller than the 90 degrees in this corner up here too, right? So that's positive strain. If you have negative strain, then what happens is this parallelogram actually expands out beyond. So you would have something coming off this direction, a little bit and coming off this direction, and then this angle in this corner and this angle in this corner, that'd be a little bit smaller, right? Just to give an idea of what positive and negative shear strain really look like. Does the material really care in terms of it's going to fail or not? No, okay, because essentially I can rotate the parallelogram 90 degrees and my x and y's flip, right? I'm going to have now positive strain describing negative strain and negative strain describing positive strain, okay? So I always think that the shear strain is a little bit more confusing to describe, okay? But the sign is less important with shear strain, but it can be significant, right, in terms of thinking about is the material element in compression and tension. Because we've discussed this prior, some materials will have a higher yield strength in compression than in tension, the brittle materials in particular. So, once again, plane strain is going to focus our attention on epsilon x, epsilon y, and gamma xy. Any questions? Yes?
You mentioned earlier the thickness. I'm not sure what you mean by thickness, because isn't this supposed to be like a surface?
Okay, here we go. Next slide. Good question. All right, good question, Jonathan. Okay, so plane strain, yes, you think it. We are looking at a surface, okay, but it typically has some infinite thickness. All right, and we're saying that the distribution of loads or the traction vectors or whatever they might be, they're the same throughout this infinite thickness. And that's what we're getting at. And this would be plane stress, typically a thin membrane. Okay, so let's ask ourselves a question: when can plane strain and plane stress be equivalent? And so you need a situation where both the sigma z and the epsilon z stay equal to 0. Okay? And if we think about the equations where we have the epsilon equal to 1 over e times quantity sigma minus nu times sigma 2 plus sigma 3, all right? Remember that constituent relationship? We get to a situation where we can have both a sigma and a epsilon z both the epsilon z and the sigma z can be equal to 0 when the Poisson ratio is equal to 0. Okay. So here we go. Epsilon z is equal to 1 over e times quantity that thing, sigma z minus nu times quantity sigma x plus sigma y. Right? If I had a plane stress condition, right, I would have sigma x and sigma y at least, right, not including the tau, right? So then that would mean that if sigma z were 0, which it would be for plane stress, I would automatically have some type of epsilon z, right? But I'm not supposed to have epsilon z if I have plane strain. So that's where we get to, well, if the nu, the Poisson's ratio, is equal to 0, then this condition can exist. But in reality, you don't have materials with Poisson ratio equal to 0. Okay, Poisson ratios are typically between 0 and 0.5. The metamaterials, have we talked just briefly about metamaterials? Well, if you Google metamaterial and you Google negative Poisson ratio, you're going to find some fun stuff. So these are usually called architected materials, where instead of when you pull it apart, the cross-sectional area contracting, it's got little buckling beams and little different geometries in it, and these are sometimes called auxetic materials, where you pull it and it will actually expand in that direction. Okay, which is opposite, right? Or you compress it and it will shrink instead of expand. Okay, so those are that's not relevant. That's for your good to know file. Okay, but Poisson ratio equal to 0. That's a hard one to do. Okay? But that would be the condition that would satisfy plane strain and plane stress being equivalent to each other. Okay. So normal strain, and you can think of when it's really, maybe I should have said this earlier, if you think, okay, it's infinitely deep, okay, the idea there is, okay, I can have some epsilon x, I can have some epsilon y, and if it's infinitely deep, then if I have a little bit of Poisson effect, because it's infinite deep, I won't see it. Okay, so that's the idea with plane strain, or one of the ideas with plane strain, right? Because infinite deep is infinite deep, very little going to happen in the in epsilon z. Okay, so normal strain, we've discussed this before, okay, represents the displacement between particles in the body relative to a reference length. And we've discussed the profiles in 2D of their strains. So this would be a normal strain. So this is kind of just review, and we've already said this. And off the y face, we'd have epsilon yy, and we would just say that we have epsilon x and epsilon y, right? So you've seen this before. This is not new information. Shear strain. Again, we kind of just discussed this, and this slide is very similar to one that we've used previously. I should probably update the ones that I have shown you previously, but I haven't gotten to it yet. So it's the same, but it's just showing, all right, you've seen all this before, we've talked about this before, okay, This is maybe the new update. I threw this diagram in here, and we already talked about this, okay? So the more precise way to describe shear strain is not to constrain one of these walls like you see here. I mean, this is not untrue, okay? It is shifting this direction, but the more precise, the more technically correct way is to draw it where it has deformation on either side, or an angle on either side, this alpha and this beta, and usually for a linear isotropic material that's elastic. Isotropic meaning, when I say isotropic, do you know what I'm talking about? No. Okay, so I'm just throwing fancy words around. All right. So what does iso mean? Huh? If you're playing basketball and someone says you're going to do iso, what does that mean? Okay, that was a bad analogy for this crowd too. Okay, huh? Yes? Yeah, it's one-on-one, right? Solo. Solo, I like that. Not Han Solo, but solo, okay? So it means iso 1. Tropic, okay, we're not going to the tropics, all right? But that's like the climate, I guess you could say. Now you've really got to try. I don't know what the Latin for tropic is really, okay? But when we say isotropic, that means uniform. Uni, right? 1. Uniform. So when we say linear isotropic elastic material, what does that mean? It means we have an elastic modulus and we have a shear modulus that's going to describe, right, that material. Linear elastic, right? The isotropic means essentially it behaves the same way in every direction. So you could have an anisotropic material where I strain it in one direction and I have a different stress than when I strain it in the other direction by the same amount, I would get a stress that's different, okay? Because the elastic modulus, I could have an elastic modulus for the x direction, I could have elastic modulus for the y direction. Yes?
Does that just have to do with the densities?
So I mean, density will play a role. The kind of the, how do you say, the most common, okay, well, let me ask you, what is a common everyday material that you know and you love that would be anisotropic, meaning not isotropic in its behavior? Any ideas? Everyday material. Okay, I need to make sure we get this. If Professor Pellegrini, no names, I guess, I shouldn't mention names, but if she walks to you in the hall and she says, name an anisotropic material. Yes?
Extra. Meaning in one direction it's going to break.
Okay, that's interesting. Okay, so that's more of a structural thing. That's more of a structural property. But I like it. I like what you're saying, okay? So the eggshell material itself, I don't think is very anisotropic, okay? But yes, the properties that result in that geometry would be, yes, it would vary, depending on whether you're doing it, okay? A material, something that I could take down to a reasonably microscale or millimeter scale, and like that's a material. Any ideas? What's anisotropic? Something that doesn't behave the same in two directions. Yes. Carbon fiber. Okay, very good. That's one example. Now, but what say more than carbon fiber? Because let's just say I have a piece of Kevlar, a string of Kevlar. That's carbon fiber, but what do you mean specifically? Okay, good. So when you are saying carbon fiber and you're looking at the exterior of a fancy new car or a bike or a fuselage of an airplane or a wing or something, what do we mean by that? We mean, yes, it has this strong material, kind of stringy, fibrous material. Okay, that's the fiber part of it. And it could be made out of glass. It would be carbon fiber if it's made out of glass. That would be fiberglass. All right, just to be clear. All right, but that's embedded in some type of epoxy typically, or it could be in a thermoplastic. All right, because you have some 3D printers now that incorporate different types of fibers into them. So yes, if I have a very strong material embedded inside of a other material, and all the strong materials are going in one direction, right? Then it makes sense that, it's going to be much stiffer, that structure, right? The elastic modulus of now, if I'm talking about the material itself, is going to be having a higher modulus of elasticity in that direction that the fibers are going. And if I want to pull the orthogonal direction, right, it's going to be a little bit less in its elastic modulus in that direction. So that's a very good example of an anisotropic material. I'm going slow because I think we can get through these slides today without too much difficulty. That's what I think. All right, so this is an informative discussion. Yes, another anisotropic material. Yes, did you say that, Prisha? Of course. You've got wood. Actually, this is probably fake wood. I think there's some real wood over there. Okay. This is probably some like pressure treated thingamabob, okay? Or plywood, right? Wood, the trees, right? The xylem and the phloem and all that jazz, right? That ends up with having a very fibrous material. And so if you go home and you get a 2x4, you'll probably be very frustrated if you try to break it by yourself, to be honest, without, do not take a 2x4 and try to break it over your head, right? Not recommended. Of any size, okay? Any length. I don't think that's a good idea. It had to be very, very, very long. Why? Because then you could get a huge bending moment, right? And you could try to get it to break where it's constrained on the ends. It will also break your head, probably. Okay, so don't do that. Okay, but have you ever splintered a pencil? Yeah, what do you see? You see all that stuff. So you could do that, right? Let's not do that either, okay? That would be a mess, right? But if I were a good professor, I would have a bunch of pencils and hand them out and say, let's go ahead and try to break them, okay? Okay, but I'm not. So that's another good example of an anisotropic material. So for our intents and purposes, we are talking about materials that are mostly isotropic. Now, let's go into not the nasty stuff, but let's hear the number or the variables. Okay, so remember those stress transformation equations? We now have strain transformation equations. Okay, and yes, I guess some of you are copying them down, But whether you copy them down or not, you can see that they look a little bit similar to what we had for the stress transformation equations. We see there's a cosine and a sine dependence. It was tau xy here before, okay? And it was sigma x and sigma y before, right here. And this was the average, right? We had an average sigma average. Now we have an average or an epsilon average here, okay? And you can see that we had the difference here in this coefficient, right? But there's an interesting factor of 2 that comes into play. And if you want to see the derivations, you can click on the link, or you can look at Hibbler's book, which is your suggested textbook. If you feel like we're not going into enough examples in depth, it maybe, I hope I've said it before, and it's on the syllabus. This is your suggested textbook. But we see that we have 3 equations for an epsilon x prime, epsilon y prime, and a gamma x prime y prime. But there's this strange factor of 2. And if you go into the derivation, that factor of 2 comes out. And if you think, when we did the pre-POMX, when we did the finite element analysis, do you remember how we were talking about, it's actually spitting out gamma over 2s, right, for the shear strain components? Remember when we had those tensors that we were looking at, the epsilon 1, 2, the epsilon 1, 3, the epsilon 2, 3? That, when we said, oh, that's just because of the tensorial math. Right? Well, here's another case where it comes out. When we look at rotations, if we want to preserve the information easily, we end up having to write our expressions in terms of the gamma over 2. Okay? So gamma over 2, right? Gamma xy or x prime y prime over 2, right? That means that whatever I spit out when I put it into my lovely calculator, I need to double it. I need to double it to get the true shear strain. We will make this mistake together. Okay, I will probably make this mistake before the end of the semester. Yes?
Does the Moore circle in this case still have the same thing with the 2 theta?
Yes.
So it's like doubling it and then having it again.
So the theta is still 2 theta because that's over here, right? But now it's just the vertical axis. Remember at that first slide, we said, look, this is your first time I'm saying it's gamma over 2. It's gamma over 2 for that axis, but yes, the angle of rotation still is going to be twice in the Moore circle, all right, or 2 theta in the Moore circle, and the material element is just the theta. All right, good questions, good points. Okay, we can also go back and say, remember we had equations that would just tell us the principal strains. We set the derivative of the sigma in that case, right, equal to 0, so we could figure out the sigma x prime, where we could set that equal to 0 and then try to find a local maxima or minima, okay? And then when we did that, we would find an angle and we could plug it back in, all right? So now you're seeing this is how you calculate the angles associated with the principal strains and the epsilons that are the principal strains. Okay? It's very similar, right, to what we've discussed previously. And we can also calculate the maximum in-plane shear strain. Okay? And these are the big equations. And on the homework, there'll be a nice opportunity to do your first one using an equation. Okay? And as we'll see in a second, trying to do the equivalent of solving these or deriving these equations through geometry or through slicing triangles would be a little bit trickier. Okay, I mean there are good derivations there. Okay, except it's not a direct balance of forces. I mean, force is still equilibrium rules, right? But remember how we talked about shear strain and what it does, right, to the actual element? And we talk about what happens with the epsilon and epsilon y, right? That stuff can be a little bit tricky. It's nice though if you can go through, right? If you can go from our stress transformation equations that we've had through constitutive relationships. What are constitutive relationships? Those are relating stress and strain with each other, right? To be able to come up with this type of derivation. So there's not going to be a question, draw and slice a triangle, and now use that to determine the principal strains. That would be not so nice. Okay. So, remember the factor of 2 difference. Okay. And I'm just highlighting some of these factor of 2s. And also highlighting the non-factor of 2s. Okay, so people, I understand, I'm saying it verbally. I debated, like, should I not put that circle there before class? But I left both of these circles there. Okay, it's not a typo that is circling nothing. Okay, it's just there is actually nothing there, and be aware that there's nothing there. Okay, that's all. And if we look at the substitutions, what we see is that tau xy converts over to, or the equivalent, I guess you could say, is gamma xy over 2. Sigma x converts, or equivalent epsilon x, or its analogous friend is epsilon x. Sigma y, analogous friend is epsilon y. Sigma x prime, analogous friend is analogous variable. Parameter is epsilon x prime. Sigma y prime, epsilon y prime. And tau x prime y prime, gamma x prime y prime over 2. Okay? No biggies here. Okay, so now let's look at an example. What is the state of strain for an element rotated 45 degrees when you have a uniaxial strain of epsilon x? Okay, so why would I pick this one? Well, you know that the uniaxial cases are kind of important and nice, because from a practical perspective, that's how we test the materials usually, right? We test them with a uniaxial loading. So if we're interested in seeing, okay, what is the strain 45 degrees from this, we can use these equations. And we can plug in what? 2 theta, so the 2 theta will be equal to 45, or would be equal to 90 degrees. Okay, so we can go ahead and plug in the 45 degrees into our equation. This one at the top, we get epsilon x prime is going to be half of what epsilon was. Epsilon y prime is going to be half as well. And we have that the gamma x prime y prime, okay, divided by 2 will be equal to the negative of a half. So that means that gamma x prime y prime is equal to minus epsilon x. So what does this kind of look like in terms of how the geometry might change? Well, you have if you have a delta x, right, you can say, okay, we have epsilon x. So that's kind of, you understand it's stretching in that direction. And now we're 45 degrees from it, okay, because we've done this 45-degree transformation. And our x prime and our y prime are sticking out. And, this is 45 degrees relative to the original element. And we now take a look at the strain. So, according to the math we just did, let's first talk about what the area of this element is going to look like. Okay. Is this element expanding or contracting in terms of area? Got 50-50. Yeah, Mark? Expanding, okay? So it's expanding. And if we think, right, look, epsilon x over 2, and, sorry, not that one. I want to use the ones for my case, right? That's right? Epsilon x prime is going to go this direction, half of what it was. Epsilon y prime is going to go half of what this value was, right? I mean, this element was expanding, as you saw, right? So this element expands. And we can kind of draw it as becoming a larger, squarish, diamondish feature. Now, what's happening though? Okay, so we can say, okay, we got this strain in these 2 directions, as described as epsilon x over 2. What is happening though with its corners and the angle in the corners? Well, we said that the shear strain is negative, which means, right, that it has to open up beyond 90 degrees at this bottom vertex. Okay, that's the vertex of x prime, y prime. Okay, and so I don't have enough flexibility. Okay, here we go. It went from this to this. All right, do we see that? Because it's negative. Remember when we said it was positive, it would go like this. Negative, it opens up. Okay, so that's what I'm trying to demonstrate with my very bad drawing. Okay, that the gamma x prime y prime is equal to minus epsilon x, and it's opened up. Any questions on this? I guess I've done this before, just in terms of drawing. But if you think about an element on a bar, okay, so now we're applying some force, and we think about an element like this. This is the element on the bar, and now I'm thinking about an element that's rotated 45 degrees on that same bar. Okay. Right? If now I say I've stretched this thing out like this, right? We can see that this element has stretched in that direction, right? Just like we said before, that would be the x direction. Okay. And this has whatever, this is x though. Okay? Direction. And we see that this element down here would also stretch out like that, kind of becoming closer to a pancake, right? And this is the x prime, and this is the y prime direction, 45 degrees. And look, what do we see? We see that let me just draw it. In this, in that corner, right, it became greater than 90 degrees, right? So that is just emphasizing, if I had a rubber sheet or I had that eraser again that someone left and I could really stretch it, this is what you would see happen to the eraser. Any questions on this? Yes, Michael.
So for stuff like this, can you think of like a problem you would ask?
Okay, a problem I would ask. Well, how about that, Michael? There's a problem I would ask, okay? Okay? Okay, here's an example. Okay, what is the state of strain for an element rotated theta from a condition of normal strains of epsilon x equal 10 microstrain and epsilon y equal 20 microstrain? Okay. Now, I'm sorry, that was a little bit tongue-in-cheek or facetious, right? But yeah, so I think maybe what you're getting at is why do I care about this, right? Like, why do I care about being able to do these types of strain transformations? Well, at the end of today, I hope it'll be obvious that if you can measure the strain, you can go back to figure out the strain in maybe a different configuration. All right, so that's why strain transformations are helpful. And if you can measure the strain, you've got some idea of what the stresses in the structure would be. And so you could determine whether or not it's going to fail according to the yield strain. Now, materials can also have a specified limit on their strain. They can have a strain limit, the yield strain, okay? So it's not as common for a material provider to say, this is the yield strain for your material, right? But if you know the elastic modulus, right, and you know the yield strength, boomba, right? You can figure out what the yield strain is going to be, right? Because you know that E is equal to sigma is equal to E epsilon, right? And if I'm interested in epsilon, then it's just SY over E. SY over E would give us the yield strain, right? So you could also look at yield strain and be able to figure out, oh, this is my yield strain. If I look at the state of principal yield strain, okay, and I exceed that, and it's uniaxial, okay, there are a couple conditions there, then I can predict whether or not I'm going to have failure just by the yield strain. Okay? Or if I have yield strain and I'm in some different configuration and I can transform it like we just did, 45 degrees, we now know what the maximum shear strain is going to be tolerable, okay, and we can calculate that shear strain, that would be another case where we figure out. So what would be a good problem? You caught me on the fly. I think a great exam problem would be, which is I think what you were getting at also, would be, here's the yield strength of the material. Tell me, what is the yield strain of the material? Well, you can say, well, I have to know the elastic modulus. Now, what is the maximum shear strain that this material can tolerate? So you have to do this 45-degree transformation because that's going to give you the maximum in-plane shear strain. Now, here is a load on a structure. Does the maximum shear strain, does the absolute maximum shear strain, does it exceed the yield strain limit that you calculated? So does this material fail or not? Okay, so that might be an example. Okay, good. Okay, so back to this simpler example, what we're going to say is there's a state of strain for an element rotated theta from a condition of normal strains of epsilon x and epsilon y. All right. So here, what we want to do is think about the strain transformation equations again. We can say that epsilon x prime is equal to this 15, okay, times, wait a second, hold on. Yeah, because I got, here we go. Okay, where did this 15 come from? Right, that's the average here. Okay, where does this difference? This is a -5, right? So we can then calculate this, and we're just saying, hey, what's the state of strain for an element rotated theta? Okay, so we can just write out these expressions like we see here, and the original elements, okay, would look something like that, with an x and a y, and epsilon x and an epsilon y, okay, drawn as you see here. And then we're saying that if we rotate by some amount, theta, okay, now we can figure out what the new state of strain might be. And assuming that this new state of strain, right, this is a positive quantity, at least the way we've got it written out. So we know it's going to pinch in the bottom corner like this. So this is just kind of a general depiction. And epsilon x prime dx prime would be in that direction, and epsilon y prime dy prime would be in that direction. Okay. And the gamma x prime y prime over 2 would be like that. Okay. So that's essentially doing the same thing we had, and we're going from a state of normal strains. They're actually principal strains because, and I should have maybe said this more explicitly, the gamma, in that case, the gamma xy was equal to 0. Okay. Questions, comments, criticisms? Okay. Okay, so let's look at another example. We have discussed how just like we have stress-strain curves, we can have shear strain, shear stress, shear strain curves, where E is not the slope, but G is the slope. Okay. So when we look at these expressions, what we have is that tau is equal to G gamma, and we can also figure out what G is by using this relationship. And we didn't derive this relationship before. We said we'll derive it later. Well, today is our lucky day. We're going to derive this relationship. And I guess it's good to point out that the shear strain, this equation, this tau is equal to G gamma, is it's very powerful, especially for the cases where you have pure twisting and pure torsion. Now, let's do this derivation. We start with an element in pure strain, or pure shear, sorry. Pure shear, sorry. So what does that look like? It looks like that. We just have tau xy. Now, what we're going to do is we're going to rotate that element by 45 degrees. Now, this is a derivation, so it's not like we're solving a problem exactly. It's just this is deriving that g is equal to e over quantity 2 times quantity 1 plus nu. Okay? So we rotate the element by 45 degrees. And what does that look like on Moore's circle? If we start in pure shear, what is the new state of stress when I go by 45 degrees? You all tell me. What is it? We're now experts at Moore's circle, right? Okay, what's that? Okay, so what about tau? So in this case, what is tau equal to? When I've rotated on Moore's circle here, right? So now I have this new state. It's a mini Moore's circle, I understand, right? But in this state, what is the, first off, is this a state of principal shear, or is it a state of principal normal stresses? Or is it a state of maximum shear stress? When I go from here, it was a state of maximum shear stress. And now I've rotated 45 degrees, and now it's a state of principal stresses, right? So there's no shear. And I have the sigma x prime here, if I go this direction, right, would be equal to that tau xy that I had here, right? And the y component would be negative, right? That'd be negative tau xy. Okay, so sigma x prime is equal to tau xy. Sigma y prime is equal to minus tau xy. And another way to write that is sigma 1, right? Because that sigma x prime is now the sigma 1, and the sigma y prime is now the sigma 2. And as we said multiple times, sometimes sigma 3 is just equal to 0, even though it's not the smallest, right? It's not the minus tau xy here. So the state of stress looks like this. Positive in tension in the x prime direction, negative in compression in the y prime direction, and 0 shear stress. Let's bring out one of our oldie-goldie equations, right? This is using the Poisson's ratio and elastic modulus to relate normal strain to normal stress. And we can then plug in epsilon 1, okay? So you see what we're doing here? We're going to say, let's plug in, instead of sigma x, we're going to plug in the sigma 1, so that's in the x prime direction. So sigma y, all right, is going to be this minus sigma 2, and sigma z is 0. So now, when I plug these things in, I have epsilon 1, which is the principal strain, okay? So that's going to be in this direction, is going to be equal to 1 over e times tau xy, all right, times this quantity. And we're like, oh, this is cool. We're getting the 1 plus nu. We're getting close, right? Because what we're trying to derive, I should have probably written that. Okay, what we're trying to derive is g is equal to e over quantity 2 times quantity 1 plus nu. Okay, so we can kind of see, hey, we've got an e, we've got 1 plus nu. We're kind of getting close here. All right, what do we do next? Well, we can write that the principal strain can be related to any epsilon x and epsilon y by this equation. Okay, and this is a state of principal strain. Okay, the way we've written this out. So any arbitrary epsilon x, epsilon y. All right. So we can go back and we can say that this epsilon 1 is equal to this. How do we do that? This is a stretch. Because in the pure shear case, so remember, we're going back now, okay, to this gamma xy, not gamma x prime y prime, because gamma x prime y prime is 0 here, okay? The gamma xy that we had here originally we had epsilon x equal to 0 and epsilon y equal to 0. And if we plug that back into this equation, we have sigma x equals sigma y equals sigma z equals 0. We're just left with the we're just left with the gamma xy in this equation right here. Okay, do you see this? Okay. I'm sorry, this is going, that's not where I wanted to plug it in. Let's do a little, oh, I didn't just do that. I did just do that. Oh no, what did I just do? No, don't do that. Yeah, okay, but I don't really want to do that. Hold on. Okay. Right, this is truth, and then we plug it down. We move. We also look at this equation down here, okay, so that we can say that epsilon 1 is equal to gamma xy over 2. And once we've done that, we can bring in another constitutive relationship that tau xy is equal to g gamma xy. Right? And remember, this is good for the pure shear case in particular. So now we can substitute in these equations with this equation with this equation here. Okay? And we start doing that, and we get that G is going to be equal to 2 over, is equal to E over quantity 2 over 1 plus U. Okay, any questions on this? Okay, so a little bit of algebra, a little bit of plugging around, messing with things, okay, and now we're able to derive this important equation. For homework, you're going to get to talk about the state of strain for an element, and we're going to do a 45-degree rotation, and you're going to have some epsilons, and then you're going to figure out what the maximum in-plane shear stress might be, or shear strain might be, and what the principal strain would have been. Okay. And now we're going to use more circle. Okay. No surprise, this is very similar to more circle for stress, but we're using it with strain. So that was more circle for stress, and this can be transferred over in terms of the equations to plane strain, and the more circle then looks like this. We have epsilon on the horizontal axis and gamma xy over 2. And you can kind of see that here. Remember this, right, x squared plus y squared is equal to r squared. That's the equation for a circle. And here it was just tau squared. But here it's gamma x prime y prime over 2. So one way to handle that, to not be drawing ellipses, okay, because that would be a possibility, right? If we just drew gamma here, all right, then we would have ellipses where this height would be twice, so they'd be elongated in the vertical direction, all right. But we're still doing circles. So to do circles, we draw them this way. And once again, we can figure out where the center of more circle is by taking the average of our normal components. In this case, they're going to be epsilon x and epsilon y. And we can go forward and think about where the epsilon x is, right, horizontally. We can figure out where the gamma xy over 2 is, and we can plot that point, make a radius, and draw the circle. Ta-da. Okay. And if we're interested in figuring out the horizontal distance, it's just going to be the epsilon x, okay, minus epsilon y over 2. And that comes from taking epsilon x minus epsilon average, right? That's what that value is coming out to. Okay? And the radius, right, will be essentially the hypotenuse of the triangle that this adjacent and this opposite side form. The opposite side, of course, being the gamma xy over 2. That's the derivation. So the second question, and I'll have more videos to help with this, is to go ahead and use this Moore circle, right, to plot and figure out, for example, what the largest principal strain might be. So if you found last night's or whatever, whenever you did the homework, but the homework due today fun, right, this is going to be more fun, but just remember that we have the gamma xy over 2. Okay? And hopefully what you've seen at this point that Moore circle is really nice for being able to calculate maximum shear stresses, maximum principal stresses, and now we'll see that it's really good for calculating out maximum shear strains and maximum principal strains. Okay, so there will be another question on Moore circle, and then we'll get into our strain gauges. So at the beginning of the class, I was trying to get everyone excited about strain gauges. So maybe I won't repeat as much about it. The basic idea, though, is that we put these strain gauges on structures to be able to measure their strain and be able to see how they're reacting to whatever the loads might be. You can put them on bridges, you can put them on aerospace vehicles, you could put them on your kitchen table if you wanted, okay? But they are going to give us an idea of what's happening on the surface of the material and what's happening also internally. As we've discussed, often the largest stresses are on the surface. Why are the largest stresses and strains on the surfaces of the objects we build? It's convenient for us if we're measuring things, but why would that be the case? Why would the stresses be the largest on the surfaces for your everyday objects? Thoughts? Yes. Let's see. Yes. Go ahead.
So you said why would the stresses be large on the outside?
Yeah. Why are the stresses largest on the outside surfaces? And strains, therefore, also largest on the outside surfaces. Think about some of the relationships that we've studied so far. Yes?
Wouldn't any force applied affect the outside more? Because it's furthest away from the center.
Okay, well let's be a little bit more specific there. Okay? Any force applied in which way?
Well, for like beams and whatnot, right? If you apply force down here, the bottom of it is the most amount of stress, and the top is the most amount of strain.
Correct, right? And so if you apply a force in a way that it creates a bending moment, and the structure is experiencing a bending moment, there's going to be some type of bending stress associated with it, right? And we know from the flexure formula that sigma is equal to negative my over I. And y is the distance from the neutral axis. So bending stresses are going to be highest at the surfaces, typically. Okay, so that's one reason. What's another reason? So I completely used math there. Give me some more math that would indicate that the stresses can be the highest at the surfaces. Hold on. I know you're all thinking, what's another situation where the stresses are the highest at the surfaces? Yes. Torsion, right? TC over J, All right, we purposely use C as the radius. Okay, so the stresses are going to be highest when you're twisting. So if you and then, okay, so we've got two cases: bending, right? Beams, plates, whatever they're bending, their stresses are the highest or the minimums, right? Depending on contention or compression at the surfaces. Shear stress and shear strain are going to be highest at the surfaces under twisting. And axial loading, for many intents and purposes, is kind of uniform, right? Throughout materials. But it turns out there's another case that you'll talk about next semester when you take design mechanical components. In corners, often you also have high stress concentrations, mostly for vibration and impact loading, and those situations are also at the surfaces. Okay, so it's kind of nice that strain gauges go on the surfaces. It's like this nice, beautiful thing that we can put the strain gauges where the most likely problems are going to be. The other thing that can happen, and Professor Pellegrini might ask you, what is fracture? And we don't cover fracture in this class. Okay? But the one sentence description is fracture describes the propagation of cracks. That is what fracture is. Okay? So, once again, what happens? Crack, where does it form? It forms on the surface initially, where the stresses are the highest. And how does it propagate? Away from the surface toward the middle. So fracture is a problema. That's a problem. Okay? And we need to understand what's happening on the surfaces. That's why people care about cracks so much. Okay? Again, something you should just get out of your mechanics class. That's why people take those. If you ever watch like some of these documentaries about plane wings that have failed, you might see like a person with a little not microscope, what are they called? Magnifying glass going along the wing looking for any cracks. Because if you have crack, it can start to propagate, meaning grow. And if it grows, guess what? The effective cross-sectional area that's supporting your loads is getting smaller. And when it gets too small, we know it exceeds the yield strength of the material in that location, and boom, that's a failure. Okay? Fracture in a nutshell. Okay, so now we got 8 minutes. That's good. 8 minutes to get through how to use a strain gauge or how to use stress transformations. So strain gauges might look like these. They're beautiful. And ultimately, you've got some type of material that you can measure a response to strain. Okay, so this material could be piezoresistive. Okay, piezoresistive means as I apply a strain to it, it changes its resistance. It's electrical resistance. Okay, so what happens when you change the cross-sectional area of a hose and you have water flowing through it and I pinch it? What happens? Does the resistance go up or down? It goes way up, right? It becomes, you had to have a high delta pressure, right, in order to now get water through that. The same principle is applying here. As you, except there's one other component to it, but we won't talk, well, I will talk about that in a second. But you can think, as I stretch a piece of metal, its cross-sectional area decreases, and so it becomes harder for the flow of charge to go through it. Okay? So that's one effect. There actually turns out there's another effect, which is kind of this piezoresistive effect, where just the shear, I shouldn't say the shear strain, but just the basic, the pure strain, right, of what's happening also causes an effect. And that can be quantified in terms of what people call a gauge factor. Okay? So this is the ratio of change in resistance divided by strain. So the gauge factor is typically written GF, and you have a delta R over delta L over L, or a delta R over epsilon. And you're like, what is delta R? Delta R is the change in electrical resistance. Okay, and what is Ohm's law? Someone I know, yes. V equals IR, right? So what you're typically doing with these devices is somehow measuring, I apply a voltage or I apply a current, and I'm trying to figure out, okay, what is the R and how is that R changing as I apply some resistance? And in measurements, that class, you'll get to build what's called a Wheatstone bridge, and you'll be able to measure that resistance. Because it actually turns out it's kind of a small change in resistance, okay, because these are small strains. So that's how a strain gauge works physically. How do we arrange strain gauges? Well, there are two configurations that concern us in this class. And this configuration on the right is the one you should know. The configuration on the left is very nice and powerful, but it is not oh, my mouse is having trouble. This one, it's just the transformation equations are a little bit harder, okay? So I would, and if you look, I have asked questions on what we call the rectangular strain gauge, okay? So here's a stress transformation equation. There are 3 strain gauges here in this rosette, okay? The rosette is the combo, okay? So it's like you go to some fast food restaurant and they give you, a few different things. 3 often, right? There's your combo, but these are all equal. Okay? There are different angles relative to each other. Well, we know how to handle uniaxial loads at different angles relative to each other because we can do our stress transformations or our strain transformations here. So look at this. For the rectangular rosette, I've got 1 at 0, 1 at 45, and 1 at 90 degrees. Okay? Strain gauge 1, strain gauge 2, strain gauge 3. In this case, I'll call it A, B, C. So, if we want to relate the A strain to the X direction, epsilon X, that's trivial, right? Because that A strain gauge is in the same direction as X. So I don't even have to use strain transformation equations. I can, right? But I'm going to get cosine of 2 theta is equal to 0. So this knocks out, and I get sine of 2 theta. I'm sorry, that does not knock out. That's equal to 1. Sorry. This plus that, this goes to 0, right? There's 0 strain, or 0 shear strain. That contributes. All right, so that one's easy. And epsilon y is also easy, or epsilon c, okay, is, epsilon c down here, okay? This one's also easy, right, because that one's in the same direction as y. The one that's a little bit tricky is the B strain gauge, okay? But you're like, why do I even want that B strain gauge? All I care about are normal strains. I don't care about the shear ones. No. We've only been able to characterize 2 of the 3 terms for plane strain. We need this one at 45 degrees to be able to figure out what the gamma. See, this is the only place where gamma shows up. We're trying to figure out 3 parameters, epsilon x, epsilon y, gamma xy. We need 3 strain gauges because they only tell us one value. 3 unknowns, 3 measuring devices that only tell us those one directions. Okay? The strains in those one directions. Any questions on this? Okay? So this is a way to put the strain gauges on your device and be able to spit out the state of strain at that location. Isn't this wonderful? And when you do this for the first time, follow the strain gauge manufacturer's instructions. They have specific adhesives that they want you to use. They have specific ways to clean and apply them because you know what? You do not want slip between these 2 devices. I mean, your device under test and your sensor, all right? Okay, so that's about it. This is the transformation for the 6060, okay? It's a little bit more complicated and you don't have to really do it. And question 4 is to look at a rectangular rosette with on a cylindrical thin-walled pressure vessel. Okay? Thank you very much. Here's what we covered today, and let's get the attendance rolling. Any questions? With a minute to spare. Any questions? Okay. Once again, it will probably not show up. I don't know, every time now I'm learning, I have to like do it twice. There it is, okay?